Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the, I don't know what number, crypto day. What second? Six. Six crypto. Yeah. Okay, well, welcome to the Crypto Day. We have 4 amazing talks today. The first one is Ron Rothblum, who will tell us about a beautiful breakthrough, constant-round interactive proofs for delegating computations. Thank you very much.
Okay, hi, good morning, everyone. So I'm delighted to start the morning with a double session on delegation. We should have even more talks about delegation. And this is, the title of the talk is Constant-Round Interactive Proofs for Delegating Computations. This is joint work with Omer, Reingold, and Guy Rothblum. And sort of because we're talking about interactive proofs, I encourage you to have an interactive talk. Feel free to ask me questions. Hopefully it'll be constant-round. Then you'll appreciate what constant round really gives you. Okay, so what is delegating computations? So the motivation is as follows. We have some weak computational device, let's say a grad student with a laptop, who wants to perform some very expensive computation. So just running it on its laptop is infeasible. So the natural solution that comes up is to use the power of the cloud. So for example, actually Amazon will sell you time on their servers to run your computations. It's pretty cheap, and it sounds like a great idea. So our grad student will send over X to Amazon, to the cloud. The cloud computes the result, Y, which is equal to f of X, and sends it back the result. Problem solved. So not quite. The problem is that we are cryptographers, and we're distrustful. And we don't want to trust the cloud that it actually performed the computation, or that it was honest in any way. In particular, it could just be make a mistake, could happen. It could be just lazy. So if this function is something that we really haven't a value that we expect it to have, the cloud could just send back that value without actually performing the computation. Or this cloud could even really intentionally be malicious. Okay, so we don't want to trust the cloud. And when we don't trust the cloud, maybe the most fundamental concern that comes up is why should we trust the cloud that indeed y is equal to f of x? Okay, why should we have this correctness? Kind of an orthogonal issue is the issue of privacy. If we don't trust the cloud, how can we send X to the cloud? But for this talk, I want to ignore that. Let's think of X as being public. And there are solutions that you can build on top using, say, fully homomorphic encryption to get also privacy. But for this talk, think of X as being public. So X is known, and we want to compute f of X. OK, so the client somehow needs to be able to verify that indeed y is equal to f of X. So it can just do that, right? It can compute f on X and check that it equals y. But of course, that kind of defeats the entire purpose, because we don't want the client to compute f. So the natural idea that comes up is to use the power of the prover or the server to also convince the verifier, the client, that indeed y is equal to f of x. So we'd like such a scheme in which the verification is much more efficient than just doing the computation by yourself. On the other hand, since we use the cloud or the prover to help us, we want that proving is also not that complicated. Okay? And this brings us to the notion of a doubly efficient interactive proof. It was the study of which was initiated by Goldwasser, Kalai, and Guy Rothblum. And the idea, as I said, is the following. So we want a double efficiency requirement. We want that, on one hand, verification that indeed y is equal to f of x be extremely efficient. In particular, much more efficient than the time that it takes to compute f. On the other hand, proving should also be relatively efficient. So not much worse than the time that it takes to compute f. Okay? On top of these two requirements, we also really want to minimize the amount of interaction. So we'd much rather solutions in which the amount of interaction is small to those in which it's large. And of course, there's practical motivation, obvious practical motivation for that. OK, so that's to be a little bit more formal. So the situation that we have is very reminiscent to that of a classical interactive proof, right? So we have a verifier V on one hand, a prover P on the other hand. They interact. And the prover is trying to convince the verifier that X belongs to some language L. As in the classical setting of interactive proofs, we want completeness, meaning that if X is in the language, then the verifier accepts with high probability or even probability 1. If X is not in the language, Now we're going to, in this talk, we're going to talk about computationally unbounded cheating provers, and we'll get into that into more detail a little bit later. So the idea is that if X is not in the language, no matter what cheating strategy you use, you'll only convince the verifier to accept with some negligible probability. Probability the verifier accepts is negligible. Yeah.
So you could also imagine a setting where you sort of trust the server to be rational, right?
Sure.
So instead of like
Right.
super malicious, so
Yes.
maybe you only care about a prover that runs in time less than the computation time. Like if he's willing to run in the computation time, he'll
Sure.
the function.
Right. That makes sense. Since you brought it up, there's also like a model that people talk about rational meaning, like in sense of money, right? So he's paid the most if he answers honestly. That's not our setting, right? In our setting, we're thinking of okay. So that brings us to the issue of efficiency. So as we said, we want the verifier to be extremely efficient. Here, extremely efficient is going to mean basically running time that is linear in the input length, regardless of what language we're trying to talk about. Okay, so just a linear time verifier basically just reads the input. And the prover needs to be polynomial time. Okay, we want the prover to satisfy our usual notion of efficiency, or the classical notion of efficiency.
So polynomial in the computation task.
So I defined, for now, I defined it in the input length. So I'm restricting myself to P, or BPP. So one thing that I want to stress is this difference between the power that I'm giving the honest prover and the dishonest prover. So the honest prover who I'm specifying as part of my protocol needs to run in polynomial time. The dishonest provers that are trying to cheat me, I'm like very pessimistic. I'm thinking of them as computationally unbounded. They can break crypto, they can do everything. Okay, so just to stress the difference between these two types of provers. And let's kind of, just to drive in the point, what's the difference between this and the classical notion of an interactive proof? Well, kind of the same, except for the efficiency. Right? So in the classical GMR type of interactive proof, we're talking about polynomial time verifier. Here we insist on linear time or quasi-linear time. And the honest prover there is computationally unbounded. Actually, you can implement it in polynomial space, but forget about that. Here we're insisting on polynomial time.
When you say classical, is that GKR? Or is that
No, that's GMR. It's like a classical interactive proof. Like IP equals PSPACE type of. And right, so GKR, which is the Goldwasser-Kalai-Rothblum paper, is exactly the paper that introduced kind of this column. Okay, so before telling you what our result is, let me mention some prior work. So in this work of GKR, they showed such a beautiful protocol that works for any bounded depth circuit. So roughly the class NC, where the verifier is linear time, the prover is polynomial time. One downside of the protocol is that the number of rounds of interaction grows with the depth of the circuit. So quite a bit of interaction. The only place I want to talk here is, this is the only slide that I'll talk about computational soundness. So a natural relaxation that you can make is to assume that the cheating prover is not that bad. So it can be arbitrary polynomial time, but it, say, can't break crypto. It's kind of a natural relaxation. And indeed, under this relaxation, we can prove very strong results. So Kirian has this beautiful protocol for any language in NP based on collision-resistant hashing using PCPs. Here by NP, to talk about NP, I mean that the honest prover also gets the NP witness for it to make sense that it's polynomial time. And in the joint work with Yael and Ran Raz, we gave a one-round protocol for languages in P based on quasi-polynomial Yahard here. And I should mention that there is like a huge, but this is kind of the tip of the iceberg. There's a huge body of work on these problems, including ranging from implementations, work in related models like random oracle, preprocessing, also very strong results under kind of knowledge type of cryptographic assumptions, and so forth.
but when you say 2 rounds, you mean 1, 2, 1, 2.
Right. So if you're counting messages, this would be 4 messages between the two parties, and this would be 2 messages. Okay, so that brings us to the main.
Those are all public coin?
So this one is public coin. This one you need, yeah, it's not publicly verifiable. Okay, so this brings us to our main result. So our main result is this kind of double efficient interactive proof for the following class of languages. So anything that you can compute in polynomial time and in some bounded polynomial space, you have such public coin doubly efficient interactive proof. Verifier is almost linear time, prover is polynomial time, and just a constant number of rounds of interaction. Okay, so that's the main result. One thing I want to stress, and this delta is just some sufficiently small constant that I'm not going to specify.
So the constant depends on delta and on the polynomial?
No, so this delta is a universal constant.
So there exists a constant delta
Yes.
such that.
Yes, and this constant round depends on the language. So if you want to run this kind of protocol for a language that you can compute in time n to the 100, then the constant in the round will correspond to the 100.
So what is this universal constant?
I don't know. I haven't checked. Potentially, you could hope for it to get up to 1. We don't get 1.
So there exists a delta
Yes.
such that every language that
Yes.
is work? Okay.
Yes.
And the delta affects the verifier's running time, right?
No, delta is a universal constant. There exists a single universal constant delta.
So if you take like n space,
Yes.
you have nothing.
No, then the running time would be some fixed polynomial.
Right.
The running time of the verifier would be some fixed polynomial.
Right,
Okay, so it's
so
also
the
a
Yes.
delta affects
Right.
the running time
Sure.
of the verifier.
Yes. Yes. And you could hope to maybe, I don't see an inherent reason why you couldn't push delta all the way up to 1. We didn't do that yet, but potentially you could.
But just so I understand, can you say that for any language computable in poly time and poly space, let's say n to the 100 space,
No, start off saying there's a fixed polynomial such that for every,
Exactly.
yes.
then the verifier runs
Right.
this fixed
So we're actually going to see like a statement that will exactly show you that. Like a general statement, not just for languages in P.
And here is not just something that connects the space and the time, it's actually the
Input length, yes, yes.
Otherwise it can just blow up
Yes.
n and
Yes, this is n is the input length. We're going to see more like the general thing, which I thought would be useful, and now I think it even more.
Just to say it in other words, if I wanted linear time for the verifier, that would dictate what delta should be.
Yes, exactly, exactly. Okay, and one thing I want to stress here is that this is an information theoretic result. So we're not making any cryptographic assumptions. We're not assuming that the cheating prover is computationally bounded. And in particular, this could be, so I'm not claiming that our protocol is practical in any way, but just the fact that you don't use crypto can many times be beneficial for implementations where crypto is expensive. Okay, so before telling you more about the proof, I wanted to say a few more things. So one thing is, how tight is this result? So somewhat tight. So if we define this class of languages IP sub,
So you said that the constant depends on the language, right? The number of rounds.
the number of rounds, yes.
So is there any example of a language that you've constructed protocols for which? No, but you mentioned implementations, right?
Mhm.
And I noticed that in these talks that somebody gave at MIT a few weeks ago, they were focusing on particular languages. I don't know what it was, matrix multiplication, what was it? Anyway, there's some languages they invested a tremendous amount of work. I'm just wondering, not for that language, but it's,
Right, so I thought actually simplified versions even of our protocol for interesting languages for which you can have a 3-round, 3 message, even not even 3-round. Right. But in general, the constant in the constant round is going to be not so good. In general.
What is this? So there's some inherent dependence, right?
Yes.
Either on the space or.
So we're going to get to that. Yes. Yes. You're talking about the round?
Yeah.
Yes, we're going to get to that. At least we conjecture that there is. It's reasonable conjecture. So, okay, so how tight is this result? So let's just define the complexity class of IP sub DE as this class of languages that have doubly efficient interactive proofs. Okay, so we have this nice complexity class. Our main result shows that it contains all languages I know it this way. So time space, poly n, n to the delta. Languages that you can compute in polynomial time and n to the delta space. So this is our main result. And on one hand, it's totally trivial that this class doubly efficient interactive proofs is contained in BPP, right? Because both parties are BPP machines. And on the other hand, it's not hard to see that it's contained in space, in linear space. Because if the verifier is linear, then in particular the communication is linear. And then at least in spirit, you can kind of, in linear space, simulate all possible prover answers. Okay, so this is kind of tight, where the gap is, one gap is kind of getting the delta to be 1. And the other gap is this kind of annoying distinction between having one machine that runs in bounded time and space and versus the intersection here, which is two machines, one running in small time and one running in small space. But up to that, it's tight. Okay, and which brings us to the kind of a general form of our main, yes?
Yeah, so if I want, so the delta does tell me something about the verifier. Right? If I want, what does that say? If I want a linear time verifier, it tells me something about the delta.
Yes.
So, okay, so in the formal statement is if I want delta to be 1, right now it doesn't mean a lot for the verifier.
It means that the verifier is going to be, rather than linear, it's going to be some bounded fixed polynomial. Yes. Okay, so let's state kind of a general result. I think it will be useful given the questions here. So let's say that we have some language that we can compute in time t and in space s. So now I'm not restricting just to polynomial time. Then for these type of languages, we have public coin interactive proofs. Now let's say, so we have this language that we can compute by ourselves in time t. Let's say that we want to use the prover to get a speed up of kind of an epsilon factor. We want to go down from t to t to the epsilon.
Is this for every epsilon?
No, this is for epsilon, which are constants.
I mean, you're saying there exists an epsilon?
No, for every constant
Every
epsilon.
constant epsilon.
Yes. So you have your language t, and you want to speed up going down from t to the epsilon. Okay? So if we want such a t to the epsilon, then as you expect, the verifier's running time is kind of dominated by this t to the epsilon. I'm thinking of the space as much smaller than the time. So this is not too bad. And in addition, I think maybe this relates to Omer's question, you kind of have to read the input. So this is kind of, in spirit, reading the input. So there's a factor linear in n.
So the trade-off is between 1, 2, 3, and 4. Right?
Yes.
In epsilon.
With epsilon. Otherwise, you could kind of, yeah. Good. So the verifier's running time is basically t to the epsilon. The prover is kind of not that bad. So it's you would hope for it to be t. It's t to the 1 plus epsilon plus a poly s factor times the poly s factor. The communication also shrunk down from kind of, okay, don't know if it shrunk down, but it's t to the epsilon. And now we pay in the rounds, right? So if we want epsilon to be very small, it's going to be many rounds. In fact, we pay exponentially in the rounds.
So again, so the delta here is the constant such that the poly s in the verifier time is less than.
Here, there's no delta.
I'm saying in generally.
So
the delta is such that the poly s in the verifier time.
Yes, it's exactly. Yes.
Is there any way, so here this result, even if you want IP for this, even IP in the classical sense, it only...
You need epsilon to be much smaller.
Exactly.
Let me skip that.
Oh.
So you can get a little bit less than a constant, but not enough to get what the other wants.
Okay, so you can't kind of...
you can't scale this up too much.
Yes.
Right, right. Unfortunately.
Can you explain? I didn't understand the other question.
Right, so a very interesting question is kind of, maybe, I'll get back to this in the, when I talk about open questions, but kind of scaling this up and even, so just kind of forget that people prove that IP is equal to PSPACE for a second. You just want to use this theorem to prove that IP is equal to PSPACE. Right, it's kind of similar. You have some bounded space language and you want kind of to improve the running time of the verifier from the exponential time that it takes to compute the language to polynomial time, which means that you want the speed up, you want this epsilon to be very, very small. And right now we can't handle that. Things blow up.
So if epsilon is 1 over log t, you're saying you would get...
So if,
the rounds will blow up, right? The rounds depend exponentially.
No, so here I insisted that epsilon is constant, and I'm hiding things going on here, which happen if epsilon becomes very, very small.
If you're able to show for 1 over log t,
so right, yes, you need so you want to move from t to poly n, right? So you need epsilon, which is the corresponding epsilon, basically 1 over log t. Right. So that goes back to this. So some dependence, as Nir pointed out, some dependence on epsilon under what I think are reasonable complexity theoretic assumptions is needed. Basically, a linear dependence seems inherent. We have an exponential dependence, and I think it would be very interesting to improve this, even to anything smaller than this. OK. So this is the main result. So just I mentioned some prior work before, just to compare how this result relates to them.
Can you move that side?
Yes.
The O tilde.
Yes.
hides polylog?
No, I'm doing it formally. So it's like O tilde of something is something times polylog and something.
Of something. So it has no dependence on
Right,
n.
right. Otherwise, I wouldn't claim constant. Yes. Okay. Right. So I just want to stress that this kind of this protocol improves on what was previously known in two aspects. So one thing is that even if we disregard the fact that it's a constant round protocol, it shows that this class IP doubly efficient interactive proofs not only contains bounded depth computation but also bounded space, which was not known previously, even if we ignore the number of rounds. And on the other hand, if we do look at the fact that it's constant round, so if we look at constant round interactive proofs with this linear time verifier, these were not known even for log space, even if you allow the honest prover to be unbounded. Okay, it was known. I think it's unpublished. So I think you and Guy had a result for NC1, or even a very uniform thing for NC1, but for log space it was not known. Okay. So before telling you about the proof, which is coming up, I just wanted to mention a few. Yes.
So right, you can think about GKR where you have like a version that where the number of rounds or the complexity grows with the space rather than the depth. Right. This is something we didn't know.
Mm-hmm.
How does this compare? It's sort of incomparable, right? It's not that you get this. Okay, so in GKR,
right.
Complexity grows with the depth,
mm-hmm.
right?
Yes.
You could hope to have a version of GKR where it grows with the space
yes.
rather than the depth. We know that some dependence on either one is inherent.
Yes.
Does this say anything about the question with the space? Like, can you get something that grows with the space and not with the depth?
That, I mean, we show that you can get it without the number of rounds growing with the space. So it's kind of even better.
But you need like a strict bound.
What do you mean a strict bound?
So I think, right, so in particular what you're saying would prove that IP equals PSPACE, and we don't know how to use our techniques to do that.
Okay.
Does that answer the question? Yeah. Okay. Okay. Okay, so before telling you about the proof, let me mention some corollaries, which I think are very interesting. So one thing that is very interesting is, so in this talk so far, we only talked about kind of the proving aspect, the soundness aspect. What about zero knowledge? So something as cryptographers we really like. So using our result, you can get zero knowledge proofs for NP, where the amount of communication is basically going to be more or less linear in the length of the witness. So instead of going through all the NP completeness reductions and so forth, you can directly get something that is linear in the witness length. This is true as long as the NP relation can be computed in polynomial time and bounded space. Okay, this previously the same kind of thing was known with bounded depth using GKR. This allows us to do this for a bounded space. A second interesting corollary is, so if you heard me previously talk about interactive proofs of proximity, so interactive proofs of proximity are interactive proofs in which the verifier runs in sublinear time. Okay, so it doesn't even read its input, and the soundness guarantee is kind of like a property testing type of guarantee. So using our result together with a result by Guy, Avi, and Salir, you can get constant round proofs of proximity where the verification or the running time of the verifier is sublinear. And you can do this for the same kind of class of languages, polynomial time and bounded polynomial space. Lastly, even if you really don't like space and all you care about is depth, we can also slightly improve the GKR result. So in GKR, we said that it's, so the GKR result holds for NC circuits, but they need to be somewhat uniform. How uniform? You need to be able to generate them using a log space machine. Using our result, you can improve that to NC circuits that are generated by, again, polynomial time and bounded polynomial space machines, which kind of gives more flexibility if you only, what you know is a bound on the depth of what you're constructing. Okay, so now let's go to the proof. Okay, so we have a language L, which you can compute by yourself in time t and in space s. That's what I mean by the time, space, and s. And now we can think of the tableau of the computation. Okay, so what is this tableau? So each column here corresponds to a configuration of the Turing machine, meaning its state and all its tapes. Okay, so that's every column here. We start off in the initial configuration, and then kind of we get an input, and the machine computes some t steps, and we get this big table. And again, I'm always thinking of S as being much smaller than t. Our goal is to construct an interactive proof for this language where the verifier runs in time that is much better than t. So here's a natural idea. Let's split up this.
So you drew it this way is the way I should look at it. Usually time goes down time, and I'm writing space.
No, so time goes this way.
Yeah, in your picture. But okay, fine.
Yes.
In all the textbooks, probably the other way. But
Does it?
first time steps, second time steps. Yeah.
Okay. Yeah? Okay. I'm using the fact that the slides are wider than they are tall. Okay. So here's a very basic idea. Let's take our t-step computation and split it up into k chunks, each of length t over k. All right, so we have these k chunks, and think of k as not being that large. And we ask the prover to send us the configuration of the Turing machine at all of these steps, right? So what's the configuration of the Turing machine at time t over k, 2t over k, 3t over k, and so forth. So these k chunks. Okay, that's nice. And now we can observe that each one of these computations by itself, you can do in time t over k in space S. So a natural thing to do is say, let's kind of recursively assume that we have interactive proofs for all of these subcomputations and run those on all of them. Kind of a natural idea. The problem is that if you think about this, if you open up this recursion, what the prover is basically sending is this entire table. Right? So in particular, just the communication is going to be t times s. We could just do everything by ourselves in time t. So this is not a good idea. Okay. Let's try something else.
You mean t over k times s?
I mean, if you open up the entire recursion, then the prover is sending this entire table. In the first step, it's sending these k, but if you open it up, then it's actually sending everything. So that's not good. So let's try to subsample. Rather than checking all of them, let's just choose a few at random and only run the, so we assumed kind of recursively that we have interactive proofs for all of these computations. Let's just choose a few of them at random and recurse only on those. Try to save on running time. So that does save on running time, which is good. The problem is that the soundness error is terrible. And the way that you can see this is just think of the cheating prover that takes the computation, does it kind of correctly until some random step. Then it does some wrong step, which leads it to kind of a weird configuration. And from there on, it does the computation correctly and ends up in an accepting state. Right? Now, if we're unlucky and we don't choose that specific block at any point of time, then we're doomed. So the soundness here is really terrible. Okay. So what would we want? We kind of want the best of both worlds. We want to verify that all k of these things are correct computations, but we don't want to pay. Right? So we don't want the k-independent invocations of the interactive proofs.
Can I ask you something? Is unrelated to just 2 slides before?
Yes.
So if you have an NP language where the witness, the thing to verify that you're verifying, given the witness is space bounded, what is your result?
You mean the NP relation?
NP relation.
Yes.
So what does your result say anything about what the complexity of the PCP? So also there, most of the work is essentially doing recursive verification of that. Did you think about that?
So
you could talk about then converting just that PCP proof for that same language.
mm-hmm.
And could look at all the parameters of the PCP proof. And has any people looked at when the verification function?
You're asking about PCPs for language with efficient circuits for verification.
I don't remember anybody looking.
So it's somewhat related. So there's the work of Yael and Ran on interactive PCPs, and then you could. So these are kind of PCPs which, after the PCP is written, to verify it, you use interaction. So that you could kind of use something like that. We didn't think about. It seems interesting. Okay, so going back, we had these two kind of very naive ideas, and we want the best of both. We want to be able to verify k subcomputations without paying k times the cost of each one. So here's the hope. So what we'd like is the following type of theorem. Suppose that we have a language L that has an interactive proof with complexity C. Think of this as the verify running time or communication, whatever you like. So we have this L that has an interactive proof. We want to construct an interactive proof for verifying k instances of the language. We want to verify that each and every one of them is in the language, and we want to do this better than the naive thing, which is running k interactive proofs. So this is the hope, okay? And we call this kind of creature amortizing interactive proofs. The reason is that the cost per instance decreases as you increase k. Okay, so like in regular amortization, right? So the larger k is, the cost per instance decreases. Okay, so our goal is going to be to amortize interactive proofs.
Okay, the complexity C is for the verifier.
Yes. Question? No. Okay, so we want to amortize interactive proofs. That seems kind of difficult. Let's try with something more basic. Let's try to amortize NP proofs, non-interactive proofs. What do I mean by that? So think of the following scenario. We have an NP language, and we have a prover which is given k instances and the k corresponding witnesses. And we have a verifier that wants to check, it's also given just the instances, x1 up to xk. And the verifier wants to check that each one of x1 up to xk is in the language. So obviously the prover could just send the witnesses, but we want a solution which potentially can use interaction. That's fine. But we want the amount of communication to be much less than m times k. Okay, so this is kind of a question that I think even unrelated to the result on getting constant random interactive proofs is a natural and interesting question. Okay, so this I call amortizing NP statements. So in fact, we don't know how to do this, and I think it's a great open question. We do know how to do this for a specific type of NP languages, specifically NP languages that have, for x's that are in the language, there's a unique accepting witness. Okay? So this is called, in terms of complexity, this is called the class UP, for unique or unambiguous NP. And the kind of canonical example for this is the promise problem unique sat, where you need to distinguish between formulas that have no satisfying assignments and formulas that have exactly one satisfying assignment. Okay, so if x is in the language, the only way that you'll be convinced is if you're given the unique satisfying assignment. Okay, so our goal now is to amortize UP statements. And here's the result. So take your favorite language in UP. We show an interactive proof for verifying k instances with the following parameters. So for the verifier, what's the verifier running time? So k times n is just reading the k input, so that seems inherent. And then instead of a multiplicative factor of m, we just get some polynomial factor in m. Instead of kind of the naive m times k, which you get by sending all the NP proofs, we're getting only a dependence kind of, we're breaking this multiplicative dependence. We're only paying m, roughly. The prover time, what can you do? You need to, the prover, was that a question?
If you get a witness for the satisfying assignment, how can you be convinced that it's unique?
Right, so it's going to be, so here you need to think of the, so this would be a promise problem, and then you'd handle the promise version of this. So you need to distinguish between the case where you have x1 up to xk, which all have unique satisfying assignments, and the case where at least like all of them either have none, no satisfying assignment, or one, but not like they don't all have one. So you handle the promise version. So this extends to promise problems as long as here you're talking about the natural extended promise. Okay, so the proof running time, what can you do? It needs to solve the problem, so it's polynomial in m and k. The communication, instead of being k times m, is roughly k plus m, which is really where our gain comes in. Right. Yes, in fact, so this poly, you can really, it's just that I don't care. You can really make this linear, I think, or quasi-linear. M is the length of the NP witness.
We should think of m as significantly bigger than n.
Yes. Yes. Okay, and the number of rounds of this UP amortization is logarithmic in k. And in fact, if you really want to insist on a constant round, you can do that, but then the other parameters blow up a little bit. So if you want this to be a constant, then here instead of having log k, you have some k to the epsilon or something. But I think this is like an interesting theorem on its own. And this I want to prove to you. Okay. I started late, right? So I have a little bit more. Yeah, OK. So how do we amortize these UP statements? OK. So let's try a the most naive thing. So we have, again, the setting that we have is that the verifier has k instances. The prover has the k instances and the k corresponding unique witnesses. And the uniqueness isn't going to come up until a few slides. So for now, think of them as just regular NP statements. So what is the prover going to do? So the prover generates k PCPs corresponding to these k statements. Just to remind you, PCP is an encoding of an NP witness in which you can verify by just reading a few locations in the proof. I'm sure you're all familiar with PCPs. So our prover generates PCPs for the k statements, this big table A. Now the verifier generates PCP queries for this PCP. And I'm going to use the fact that in many known constructions of PCPs, the verifier queries, the place that you look at, don't depend on the input. So of course, when you get back to the answer, you will look at the input. But just the places that you ask are kind of a distribution that doesn't depend on the input. OK, so our verifier generates basically this kind of the queries once. These queries are, in a sense, good for all of the k statements. Sends over the queries to the prover. These queries kind of specify columns of this matrix. And the prover just sends back the matrix restricted to these columns, so A sub q. Now the verifier checks that the k PCP verifiers accept all of these answers. OK, very simple protocol. So one thing is that it's really, really efficient. So the communication is just something like order k, maybe the queries is log m or something. So it's really efficient. But we have first try here, so it can't quite work. And in fact, it doesn't. The problem is that it's totally insecure. The reason is that the soundness guarantee of PCPs only holds if someone first writes down the PCP, then can't change it anymore, and then you go and do your queries. Here, sort of the honest prover, that's how he worked. But a dishonest prover, first sees the queries and then can generate the PCP. So if you think, and in basically all PCP constructions, this has to break, and it does. So this is entirely unsound. After you see the queries, you can easily generate a PCP that will make these queries accept. So that's not good. What we'd really want is for the prover to first commit to the PCPs that it constructed. Unfortunately, we're not in the cryptographic regime. We don't have commitments. What can you do? Try to do the simplest thing possible and see what happens. Yeah.
If we were in a cryptographic regime, does everything become easy?
Yes. I mean, it's easy because Killian did it 20 years ago. Okay. Yes, but yes. OK. So I mean, if you right, yes. OK, so let's try to do the simplest thing that we can. We want to somehow have the prover commit to these PCPs. We'll do the kind of stupidest commitment that you can think of. Just take an XOR of all these PCPs. Let's call this C for commitment or checksum, whatever you like. So just the XOR, bit by bit XOR of all of these PCPs, column by column. And this C is pretty short. So we're going to send C over to the verifier. OK? So we send this XOR. Let's just denote it this way. So the prover sent over C to the verifier. And now we repeat the previous protocol. So the verifier generates the queries. These queries specify a subset of the columns. The prover sends over the columns. But now, given this commitment, we can do an extra check. What check? So we got these columns. Now we can compute their XOR ourselves and compare with the commitment that we got. Okay, seems kind of too naive, but we're going to argue something useful about this protocol. Okay, it's not going to be sound as is. Okay, but this is the protocol.
And it works with an arbitrary PCP?
Which has this property. Yes. 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 And in particular, if you use a PCP with, let's say, quasi-linear length proof, then you can get, instead of, like, the length of what you send is almost linear in the original witnesses. OK, so this is not sound. It's too simple to be sound. But still, we'll show that it is sound if you make two relaxations, which will motivate how we'll change the protocol. So let's make the two following relaxations. The first one, I want to assume that, sort of for soundness, I want to assume that only one of the inputs is not in the original language. And kind of this seems to be a good assumption, because intuitively, this is the hardest case. Right? If there are many inputs not in the language, somehow in spirit it seems easier. So only one of the inputs is not in the language. The second assumption is the problematic one. So I'm going to assume something about the behavior of the prover. What I want to assume is that when the prover opens up this A sub q, right, the answers to the PCP queries, on all of the inputs except for the jth row, this xj star, it answers according to the actual PCP. Okay, it doesn't make up other answers. So these are inputs that are in the language, but the way that the prover acts is it answers according to the correct PCP. It doesn't make up other answers that will make the verifier accept. Okay, and then we call this a single deviation prover. It only deviates on the kind of wrong input. Okay. And I just want to stress that this is really like a mental experiment. It's a totally unrealistic assumption. Once we tell the prover not to do something, that's exactly what he's going to do. But this will motivate the changes that we'll do. So what I want to say is that indeed in this setting, this string C that we sent over does commit the prover to a PCP for xj star, the input that is not in the language. Which PCP? Just take C and XOR it with all the right PCPs for the other inputs. And in what sense is this a commitment? The way that the protocol is built, the extra check with comparing to the XOR, together with our assumption on the single deviation, means that the answers that we get on AQ have to be consistent with this PCP pi. Right? So here I'm not really using unique. I mean, it's right. Right, but I could have changed this assumption to say that the cheating prover sends like the lexicographically first PCP or something. This is not like the real place. It is to an extent, but not the real place. Okay, so for these kind of under these weird relaxations, this will actually be sound. So we got a PCP that was kind of written in advance before seeing the queries. This is the PCP for xj star, and the prover manages to convince, kind of in a PCP, you send the queries after the prover is committed to pi, and the verifier accepts the PCP. So this will be sound under our relaxations. Okay. Let's try to improve this. And the way that we'll improve it is to use a more elaborate commitment. Instead of just doing this XOR, we'll do something a little bit more sophisticated.
So wait. Just cast in terms of the previous stuff.
Yes?
You're saying if it was real PCP model, we commit to it. Okay? Now so we're not committing to it. But you're getting some sort of partial commitment. What are you saying? That if
you're getting a commitment if the prover is well behaved.
But isn't that
I mean,
behaved, but not on that, in some sense, not on the.
Not on that. It's sort of well behaved in the protocol. Behaves in. It's only allowed kind of partial power. It's not anything useful.
But it's a commitment.
It's a commitment, right? And that's for that in that setting. Yes.
So what could the prover do, right? I mean, so these things, these instances are in the language.
Yes.
Maybe there are many PCPs.
Exactly. So it's not even many PCPs. It's many answers to these queries. So think of the Hastad PCP, in which is just a linear equation. You can kind of do anything that satisfies a single linear equation. Gives you a lot of power.
So here it's important that this was unique.
Kind of, but not. This is not the real place. What's important is that I needed kind of something like uniqueness to define what it means for the dishonest prover to behave kind of on the inputs that are in the language to behave in a particular way. Right? So you could say that I'm using the fact that it's unique, so he has to behave that way. I could have otherwise defined it that what he sends is consistent with a lexicographically first PCP. I mean, so this is not yet the actual important place.
Wait, so you're saying that the choice of the witness for the honest proofs cannot create a malicious behavior on the soundness? Like only J star is...
So I'm not even assuming, so we're talking about soundness. So the chain prover doesn't even get witnesses, right? You can just brute force and find all of them. And now I'm saying, so here what I'm saying is because we're talking about like unique witnesses, I'm saying the cheating prover has to work with those unique PCPs. Alternatively, if we were in a different setting, I could have said like some canonical first PCP. This is not yet. It's coming up, the uniqueness.
That means that your second bullet here literally means not just that it's honest on the remaining guys, but also uses a specific witness.
Sure, yeah, right. And in the case of UP, this is the only witness. Yes. Okay. So let's try to improve this. And the idea is, as I said, to improve, instead of using this very simple XOR checksum, let's do a little bit something a little bit fancier. So we're going to use an encoding E, which will apply, again, column by column. So it takes the k bits, which are kind of just a column, and map them, shrink them into something like d bits. Okay, so it takes the column from before and shrinks it to d bits. And it has the following property. So if you take any two x and y's, which are a distance d or less, or distance less than d, their encoding is different. Yes. It's very easy to construct these encodings. You can do it efficiently, and in a sense, it's tightly related to error correcting codes. Okay, so this is the type of encoding that I want to use. Okay, so how do I use this? So now when the prover generates, the Onyx prover generates the PCPs, now instead of just doing an XOR, it computes this fancier encoding to construct a somewhat taller matrix C, but still not that tall. So it's D times M, roughly. And think of D as much smaller than K. Okay, so we just encode column by column as before. Yes. You could use a randomized encoding, but no reason to. Okay, so now again, the prover sends over this more elaborate commitment over to the verifier. The verifier generates PCP queries, reads the columns, get back the responses. And now, as before, we can, given these responses, we can check consistency. We can compute the encoding by ourselves, so it's important that it's efficient, and check consistency with what the prover sent over back here in C. Okay?
Wait, can you go back? Sorry.
Yes.
So you give the C is the XOR of all the long column now.
It's not an XOR, it's an elaborate, fancier commitment.
Oh, okay, so sorry. The commitment is just that encoding of
Yes.
these.
Maybe the easiest way to think about it is take A, apply an error correcting code, which has the property that it's kind of systematic, meaning that the first K bits remain the same. So you only have like these kind of checksum bits. Yeah. These are going to be the checksum bits. And you send over the checksum bits.
Just the checksum bits.
Yes. Yes. And the important thing is that these checksum bits are not that many. It's just much less than K. Okay?
Sorry. And then you send a few of the, you send the complete things and you check consistency with the case.
Yes.
Okay.
Okay. Okay, so now let's think about our cheating prover, our poor cheating prover. So it has kind of two options when it opens up this A sub Q. One thing it can do is to deviate, meaning send stuff that is not consistent with the unique correct PCPs on less than D of the rows. For now, let's keep the first simplifying assumption that there's only one input not in the language, but it'll be easy to get rid of that. Yes. Yes. So now I'm kind of separating between what if it lies on less than D, corresponding to our assumption, and kind of morally or intuitively, because we have a commitment of length D, and if you think about it, it kind of makes sense the way that we built the commitment, that if the cheating prover deviates on less than D of the rows, we should be okay. And it requires a proof. It's not too hard. The other option that the prover has is to deviate on more than D of the rows. And now something really interesting happens, because the fact that it deviated on the rows means that even for kind of D minus 1 or so of the inputs that are in the language, it sent answers to this A sub Q was inconsistent with the unique PCP for these inputs that are in the language. This is something really interesting, and this is in fact something that we can check. How do we check? The verifier chooses at random K over D of the rows, specifies them to the prover, and now the prover has to open up the entire PCP for these rows. Okay, send the witness and the entire PCP for these rows. And now we know that, so if we're in the first case, what we had so far kind of handled that. If we're in the second case, then with high probability, when we choose, let's say, we choose 1,000 times K over D statements, with high probability, we'll catch a row, which this row is still something that isn't the language, but it's on the row in which the prover deviated, meaning that it answered the PCP queries in a way that is not consistent with the unique correct PCP.
So here already, I mean, although it's a trivial point, here already, if you had more space than linear, then the verifier would not be linear. But I mean, it's just a silly.
What was more space?
The whole PCP, right?
Right. So the running time of the verifier is going to correspond to the PCP.
That's right.
Yes.
But you are working within those guys, which.
Yes. Yes.
But how do we know? You're saying, what do you mean by there's a unique PCP? I mean, how do he used he used another PCP. Now, how do I know that that's not the?
So there's a unique accepting witness,
Okay,
right? Because we're in UP. So he sends over the unique accepting witness.
Okay,
Given that, I can even say efficiently compute the PCP. And I can see,
I see.
right? Because computing the PCP is efficient, given the witness. In fact, the witness, the PCP typically contains a witness inside.
Right, I see. So you're saying, okay.
So I can, right. So now with high probability, I chose a row on which the prover deviated. Now the prover is screwed, right? So it needs to open up.
So you rejected
Yes.
found that.
Yes. Okay. So just to explicitly state what the protocol is. So this is what we had so far. Now, in addition, I choose a subset of a size roughly k over d of the rows. It specifies a subset of the rows. Send it over to the prover. And the prover opens up, right? It opens up the entire PCP on these rows. Okay, what do I check? First of all, I check that these PCPs are kind of accepting, correct, and they're consistent with the answers that it opened up over here. Okay, for those PCPs. Yes.
So the one is actually trivial, right? You're saying he cannot deviate on less than 3 rows because then
I mean, it requires an argument, which is right,
because the syndromes are different in that case.
You need to construct, like for this wrong input, you need to construct a PCP, and it requires a tiny bit of work. I wouldn't call it trivial.
Why do you have to send the PCP? Why don't you just send a witness?
And then, sure, you're right. Or send both.
I mean, the witness and the randomness maybe or something.
Like randomness for generating the PCP, typically the generation is randomness.
To check that the answers were correct. I mean, just send the witness. You know?
Yeah, you can just send the witness.
So, yeah, over here, sure. Yes.
And that doesn't blow up the verifier's time to create, like...
You can actually generate, given the instance, you can generate the PCP very efficiently. Yeah. But in fact, it's easier, right? You can send both the witness and the PCP, and then, all the computation that we use to generate, and you can verify this extremely efficiently. Okay, so this was kind of, I hope this kind of convinced you that this is sound. What about complexity? So communication, which is kind of also related to the verifier's running time. So just sending over this commitment C, it had roughly D rows and M columns. So this is just sending that commitment. So for now, think of it as square root of K. Of K. Okay? So this was just sending the commitment. This is kind of just for the PCP, K PCP answers. Think of a constant query PCP, though it's really not important. And then just opening up, I chose K over D of the PCPs and ask the approver to open up. So that's for that. If you kind of play with it, you can set D, which is square root of K, and you get, instead of the kind of trivial K times M, you get square root of K times poly M, which is already something highly non-trivial. Okay? Okay, so that's kind of a square root of K amortization. Actually getting this, improving this is relatively easy. So if you think about, so what was expensive? The expensive thing was kind of when the prover opened up the entire PCPs. So we want to avoid that. But what did we actually want to check? So we chose the subset I of the rows. And for each such row, we wanted to check, one, that the corresponding instance isn't the language. And two, kind of the consistency, that the PCP of that instance at a few particular points is equal to a few particular values. Right? That's what we want to check. So what we actually got are just K over D, slightly more complex instances, for which are themselves in UP. Why are they in UP? Because given the witness, you can verify these two conditions. Given the UP witness, you can verify these two conditions, that xi is in L, and that the PCP of xi at a few particular locations is equal to some particular values. Okay, so these statements are also in UP, so just solve that by recursion. Okay? One thing to make note, so you need to be a little bit careful. So if every time you do this, you re-encode with the PCP, you're going to get an overhead that you can't handle. So you don't want to do that. But what you can observe is that the original PCP that we had for xi is also a PCP for this more elaborate language, right? So it's certainly a PCP for checking that xi is in L, and it's also a PCP for checking this condition because this condition just says that the PCP of xi at some points is equal to some values. So the original PCP is still a PCP for this new, more complicated statement, albeit with a slightly higher query complexity. No, the place that I use it that's unique is when I ask to open up. Right, so this is kind of a crucial point. So let's go back. So over here, we said that the prover has two options. To deviate on less than d of the rows, that's fine. If the prover deviates on more than d of the rows, then the way that I want to catch him or her is to choose k over d of the rows and ask the prover to send me PCPs. Now, if he has the flexibility to choose whatever PCP he wants from a very large family, he can't do this. He can't send PCPs that are consistent with the queries that I previously sent.
So here it's actually much easier to think of the witness.
Yes, in the opening phase. Yeah. Okay. Yeah.
One also requires unique witness, right? Like the first part also requires. Otherwise, you.
I mean, it's just defining deviate.
Ah.
Just to define deviate, you need some notion. Yes.
So probably don't need a unique witness, but bounded number of witnesses.
Sure. Yes.
Do you have a PCP where if there's a unique witness, then just if the fact that the answers to the queries are verifying, then it means that these answers are unique given the queries?
So that's called the free bit complexity in PCP terms, and I don't think I'm not sure about it, but
if you use such a thing, then you can just like send the answers to the specific PCP, right? You don't need to.
Right, but I don't think so. Certainly, the constructions don't have that. They get not that far. They get that there are like 2 or something options, but yeah. I think maybe we had an argument for why you can't have it exactly, but I'm not exactly sure.
So where do you use the fact that there's only one statement that's not in the language?
Right, so I didn't actually use it. That's a good point. So it was more kind of, it was easier to describe that way. So the way that the actual argument would work is saying, if there are more than D statements that are not in the language, then basically this step takes care of that. And if there are less than D, then kind of these same things work. Right. So that's how I get rid of that assumption. The question was, so I had 2 assumptions. One was the kind of harsher assumption on the single deviation, and the milder assumption was that there's only one input not in the language. Now I'm saying you can easily get rid of that. So if there are more than D inputs not in the language, the subsampling will be fine. And if there are less than D, then these kind of things are good enough. Okay, so I'm a little bit short on time. So this we did, right? Okay, so this is just repeating the parameters that we just proved, what you can get, okay, using the recursion. Okay, so far we were talking about amortizing UP statements. To get our constant round interactive proofs, we need to amortize interactive proofs. In fact, also here, we kind of know how to do that, depending on your definition. But anyhow, to extend the ideas of what we did for NP for the setting of interactive proofs, we need extensions of the notion of PCPs and of unique witnesses to the setting of interactive proofs. Okay, so in the non-interactive case of NP, we had this notion of UP, unique NP, and we have the notion of like local checking, which is PCP. And now we need to introduce corresponding notions for the case of interactive proofs. So we call, for the unique thing, I'll define it in a second, we call it unambiguous interactive proofs, and you'll see why. And for the interactive case, we call this probabilistically checkable interactive proofs, which is related but different from the notion of interactive PCPs of Yad and Ran. So let's talk about both. I think they're kind of both interesting notions, even independent of this work. So what is an unambiguous interactive proof? So in a standard interactive proof, we have completeness in sums, right? So if X is in the language and we interact with the honest prover, we accept. X is not in the language, whatever the cheating prover does, we reject. In an unambiguous interactive proof, sort of there's this kind of unique honest prover strategy. In what sense is it unique? So if you think of X that is in the language, but at some point, this supposedly honest guy sends a wrong message, not according to the protocol specification, then with high probability, at the end of the protocol, the verifier will reject. Okay, does that make sense? And kind of we actually have, like, many of our protocols actually have this feature. So for example, in the sum check protocol, classical protocol of LFKN, land, Fortnow. Sorry?
What's an ambiguous one?
An ambiguous means that sort of there are many, if X is in the language, there are kind of many messages that you could send, and the verifier would still be still accept.
Okay, so unambiguous means that even when X is in the language.
Yes.
If you do not follow the protocol,
Yes.
you will be caught.
I mean, you need to be.
It's important to you that it's the coins from that point on. I don't.
It's kind of technically it's important, but one thing that I do want to stress is what does it mean to deviate from the protocol? So you could, like, a prover strategy in general specifies for every message what message to send back.
Right.
And certainly there are prover strategies which are different from the honest prover, which will still make the verifier accept, because you could change the prover strategy saying that if I get the coin 00000, I'll send some weird message.
Right.
So what I want to stress is that this is kind of a deviation in practice. You actually sent a wrong message.
Okay.
Okay, and so the sum check protocol, and every round, so whether X is in the language or not, it's kind of checked. The prover sends over a polynomial. If at any point the prover sends a wrong polynomial, then from that point on, with high probability, the verifier will reject, because these polynomials have a kind of large distance. And another thing that I want to stress is if you think about this kind of notion restricted to just a single round and deterministic, then this is nothing more than the class UP. Right? So the honest prover, it's kind of the NP prover, has a unique strategy of sending some witness. If it sends any other witness, the verifier will reject. Okay? So that's unambiguous interactive proofs. That's one notion that we need. The second notion that we need is an extension of PCPs to the realm of interactive proofs. The idea here is, so it only makes sense for public coin interactive proofs. So all the verifier does is send over random coins. And now at the end of the interaction, the verifier would like to check some condition on the transcript. The restriction here is that checking this condition only makes few queries to, say, each message in the transcript. Okay, so we run like any old public coin interactive proof, but at the very end, instead of reading the entire transcript, the verifier only reads parts of the transcript. And if you think about it, again, the restriction to just one round, sending over one message, this is basically just a PCP. Okay, so it's kind of a natural extension. It's actually, I just saw a couple weeks ago on ePrint a paper of Bensason, Chiesa, and Somer, I'm not sure, which introduces, I think, an equivalent notion which they call interactive oracle proofs. But it's basically the same. And let me just mention, without going into details, is that we need kind of to combine the two in order to apply all this machinery that I showed you. We need both unambiguity and this local checkability, which sounds kind of paradoxical, because what if I deviate on just like one bit? How will you ever catch that? So we need like a robust notion that deals with that.
Why is that a new notion? I'm not sure.
Which one?
This notion. I mean,
this one?
The verifier, you can read whatever he likes. So, I mean,
Right. So you could say that about PCPs too, right? You have an NP witness.
Yeah.
The verifier could read all of it, could read parts of it, right?
Yeah.
Just like, I don't know. It's,
So in any case, this isn't required. You're saying you could accept. The point is you can accept languages without reading the whole thing.
yes, yes.
No, but it's important because the runtime of your verifier, the complexity that you get at the end, kind of depends on how much you actually read, not on how much you send. So.
Right. Right. So the way that we measure, so typically we count, when we count the complexity of the verifier, we count like just getting a bit on the communication stream. We count it as like work.
Yeah.
Here, for this model, it's not, of course, not for the main result, but in this model, we have all this long interaction.
So you're saying you're introducing a new parameter.
Yes, like kind of the query complexity of the verifier.
New parameter.
Yes.
Which is how many bits you actually have to read from the final answer. Okay.
Right.
You're saying that's a parameter of interest, maybe.
Yes,
Some,
and
let's say the Chiesa, whatever I'm guessing. Let's say that
yes.
if you really wanted to. Okay, got it.
Right. And in particular, when I talk in this model, when I talk about the verifier's running time, I won't count the communication as part of the running time. Only the verification at the end. I'm not like suggesting this as like an actual model, like for delegating computation or anything, but that's how I kind of think about it.
Somehow to me it seems like instead of saying that it's a model,
it's a new parameter.
let's say it's a new parameter.
Sure.
The model seems like you're cheating. A parameter seems actually
Okay.
what you're doing.
Yes. Okay.
I mean, I don't know.
Okay.
Can you say why?
The prover doesn't see the verifier decides where to look only in the very end. The
Yes.
coins that he sends during are just to help the prover compute the next message.
To help it and to get sounds, right? We need, yes. But I mean, you're right that I allow the verifier to toss more coins after getting the last message from the prover. Or if you want, you can kind of add a dummy round, which is useless.
You don't force the verifier to reveal where he looks at a certain piece.
I mean, I could. I could also do that because I could kind of add I could send over my, like at the last round, I'll send over my PCP queries, and the prover it's too late for him. Yes.
What's the power of these two notions? Do they do all of PSPACE or?
Right. Yes. So first of all, we show a transformation, transforming interactive proofs to have this structure reading kind of few bits in every message. And if you do the thing that Shafi didn't want to do, which is count the verifier's running time, not counting the communication phase, then you can actually do kind of better things. Because you can get like right? Because I'm not counting the verifier's communication. I can do even potentially more.
Okay, let's let Ron wrap up.
Yeah. Oh, sorry. So, how much time do I have? Nothing? Minus?
Let's let you kind of.
Okay.
Questions
Okay. Okay. Great. So we talked about amortizing UP. Now we talked about these notions that we need for amortizing interactive proofs, or these probabilistically checkable, unambiguous probabilistically checkable interactive proofs. And just to recap, the idea was to assume that we have these kind of creatures for computations of length t, and now to use amortization to get unambiguous PCIPs for length k times t computations, where the idea is first the prover sends over the k intermediate steps. Now we have kind of k unambiguous PCIPs for each one of these sub-computations. We amortize all of them, and overall we got an unambiguous PCIP for the entire k times t length computation. Question? No. Okay, no questions. So one problem, I'll do this kind of briefly. One problem that we run into is when doing these amortizations one on top of the other, the query complexity, which corresponded to the fact back in the amortization, at every round of the recursion, our query complexity increased. There it was enough, it was not that bad because we were only doing one amortization. Here we're doing amortizations on top of amortizations on top of amortizations, the query complexity explodes. So we actually need an additional transformation which takes an unambiguous PCIP and kind of kills off the query complexity, reduces it significantly. This is kind of a query reduction transformation. It uses kind of PCP-like techniques. I won't have time to show you that. Just kind of the broad picture is the way that we get the computations is starting with kind of protocols for very short computations, just trivial protocols. We do an amortization step to get a longer protocol that increases the query complexity. We do query reduction. Now we do another amortization, query complexity increased. We do a query reduction, and we do this kind of balancing between the length of the computation, number of queries, and communication complexity. This is kind of in a similar spirit to the zigzag product construction and Irit's proof of the PCP theorem. No, just try to say that you need it, that it's like an additional, yes.
Is there one word you can say about the idea of the PCP that you use for this?
Right, so kind of the basic idea is to add another message at the end where you kind of send a PCP of the, let's say for now, a PCP of the entire transcript. And then what you need to check is that this PCP is accepting, that's few queries. And you need to check consistency of that PCP with all the messages. And because these are all under like error correcting encodings, you can do this. You need like a specific kind of sum check like protocol to do this, but you can do it. Kind of checking consistency between two polynomials on some fraction of points. It's actually a little bit more complicated with that, but it's not like I don't think it's like the main contribution of this work. Okay, so just to summarize. So what we showed, or what our main result is these constant round interactive proofs with linear time verification for polynomial time and bounded polynomial space languages. We introduced these new concepts of amortizing, NP, IP, and so forth. These unambiguous interactive proofs and probabilistically checkable interactive proofs. And just for some open questions, so going back to Yael's question, so can we scale up this protocol to get IP equals PSPACE? And this is not interesting only because we already know that IP is equal to PSPACE, but a more kind of refined question is whether we can get IP equals to PSPACE where the prover's running time corresponds to the computation, the time it takes to compute the language, which is something, so our result gives this for polynomial time, but I think it would be extremely interesting to scale this up. And I think there's a $100 prize for this, right? By Ed. The second question, which I think is of independent interest, is getting amortization for NP statements. And lastly, in our protocol, we said that the number of rounds depends exponentially on 1 over epsilon, which is something we'd like to improve. And the space, as I told you, there's this polynomial dependence on the space where I didn't specify the polynomial. And it would be great to get it down to linear. That's it.